All right, so much of our course revolves around structures and how structures afford function. So we're going to build on this slide in this video from last time that talked about the structures of fatty acids, and we're going to understand how that structure imparts function. So just as a reminder, here were the fatty acids that we looked at in our last video and last class. We looked at them here just as skeletal or Lewis structures here. So now we're going to look at them as space-filling models, and I have physical models to kind of show here so we can think about how their structure affords their function. So remember, when we're talking about any fatty acid is going to have a hydrocarbon tail, very hydrophobic, and then we've got a hydrophilic head group. Okay, and what we do when we make triglycerides, and over here, we're going to have a structure of a triglyceride. This is going to be of a saturated fat. Okay, what happens to sort of build this is we're going to take 3 fatty acids. So 3 fatty acids. We're going to hook them onto a glycerol backbone. So identify here was our glycerol backbone. So glycerol backbone. And just to draw the structure that we have for glycerol, glycerol is 3 carbons, okay? Triol, so 3 alcohols, right? We're going to have an extra carbon here, or hydrogen there, 2 hydrogens, 2 hydrogens. So those are my 3 knuckles. Now remember, we've got a carboxylic acid functional group at the end of our fatty acid. When you react a carboxylic acid with an alcohol, you get an ester. So essentially, that's how I attach my fingers to my knuckles. I attach my fatty acids to my glycerol backbone is through an ester linkage. So we mentioned this in our last video. Even though we don't really talk about linkages in terms of making a polymer with our fatty acids here, I will use sort of our description of a linkage here. And I do want you to think about that it's an ester linkage that holds these fatty acids onto the glycerol backbone. All of these linkages are super important, whether it is the phosphodiester linkage that we have in nucleic acids, okay? We don't really consider those from a dietary standpoint, so the next 3 are really important here. When we talk about proteins, and we've got an amide or a peptide linkage that hooks amino acids together, or we talk about the glycosidic linkage that we have that holds simple sugars or monosaccharides together to generate polysaccharides, or now we've got an ester linkage that hooks fatty acids onto our glycerol backbone. When we talk about digestion of fuels, the only way you can get things out of your digestive tract is if you start breaking these apart, breaking these linkages and getting them into their monomeric forms. So amino acids are what come out of your GI tract. Monosaccharides are what come out of your GI tract. And we can't have triglycerides come out of your GI tract. You have to at minimum break one of those ester linkages to get free fatty acids or diacylglycerides that come out, okay? Triglycerides do not come out of your GI tract. Okay, so that being said, let's return here and look at our saturated fat here. So I'm going to just kind of highlight here. We've got our 3 hydrophobic tails that we have there, okay? This is going to be a saturated fat. And in this video, we're going to talk about why it is a saturated fat, highlighting when we take 3 fatty acids, we put them on a glycerol backbone, you are going to get a triglyceride, triacylglyceride or triglyceride, abbreviated TAG is typically how I do it. You may see it abbreviated TG elsewhere. But what we're going to do here is we're going to talk about why certain ones of these may have the physical properties that they do, okay? So again, we've got 3 fatty acids here, and if we consider them all to be saturated fats, I've got some models here that I kind of want to show you. So here again is a saturated fat. So I have got a C18 fatty acid. I've got a little blue dot here at carbon 9. Maybe you remember from our last video, if we were to have units of unsaturation, they never occur until carbon 9. That's the first position we can start having a double bond on. So 1, 2, 3, 4, 5, 6, 7, 8, carbon 9. And then this is C18, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is C18 saturated fatty acid. And one of the things you'll notice is when we have all sp3 hybridized carbon atoms, this is allowed to sort of pretty much adopt a linear structure, right? We're going to have all of these carbon atoms in a row, and because there's free rotation about those sp3 hybridized carbon atoms, we can adopt the most conformationally kind of forgiving structures, which is going to be our zigzag structure that we see in skeletal structures. Nice linear sort of arrangement. Now, what that means, this is easier to show with my fingers. When we have three fingers that are nice and straight, we are going to be able to have strong intermolecular forces. So again, if we're considering what we have here with a saturated fatty acid, okay, what we will have is we will have increased intermolecular forces that we have between these saturated fatty acids. Remember, those intermolecular forces are going to be London dispersion forces. London dispersion forces are dependent on the shape, size, and surface area that we have for atoms that touch one another. So if I've got three linear fingers here, they're going to be very tightly packed together, high intermolecular forces, and that is going to lead to an increase in the melting point. Remember what a melting point is. The melting point is going to be the temperature we would need to be at in order to start disrupting intermolecular forces and take something that's sitting very still as a solid and allow it to roll around on one another as a liquid, right? We talk about intermolecular forces being like molecular Velcro. So the tighter that Velcro is held together, the more energy, that is, the higher the temperature we're going to need to disrupt that Velcro and allow those molecules to move around one another, transitioning from solid to liquid. So what does this all mean? I'm going to take this glycerol backbone and sort of move it up a little bit here. What this means is that when we talk about saturated fats, they are going to tend to be solids at room temperature. So solid at room temperature, which means we would define them as being fats, right? When you think about a fat, you think about something that is a solid at room temperature. Okay? So what I'm going to do now is we're going to highlight everything else that's on this sheet here. I'm going to highlight here in red. Okay? Because now we start talking about adding in units of unsaturation into our fatty acids. So same molecules that we sort of had over here. Okay, we're going to have oleic acid, which has one double bond, and then we've got an omega-6 and an omega-3 fatty acid. So that's what we have here. So I'm going to highlight here in red every time we have one of those double bonds. So again, what we have here is a double bond. Every time we have one of those double bonds and it is in the cis configuration, that's going to cause a kink or a bend in that structure. So let's see if we can do this here with my structures. So again, here's my saturated fatty acid. So what I'm going to do is I'm going to replace this from this point down with molecule that has double bonds. Okay, so what I'm going to have here, so this is carbon 9, you can see there's a double bond that's there. Okay, and what I'm going to have, hopefully you can see as well, there's my double bond. My hydrogens are on the same side, so this is in this cis configuration. Here again, I've got a carbon atom that's sp3 hybridized. Anytime we introduce multiple double bonds, what we're going to see is they're never in conjugation. So I've got an sp3 hybridized carbon atom, and then here's another double bond. Another double bond there. You can see it is in the cis configuration. My hydrogens are on the same side. So what I've actually made with this molecule here, we're going to go through the rest of these. I've made my linolenic acid. I've got 3 double bonds that we have there. Okay. So when I have this, and I'm going to attach it back on here. Now, these structures are a little bit floppier than we'd like, okay? But what we see is I still have, with all of these sp3 hybridized carbon atoms here, I still have the ability to have a nice sort of straight shape from the top end of my molecule here. But then as soon as I start having these cis double bonds, what really happens, and I've got weight from my molecular structure here, but in reality, what's going to start happening is I'm start to have this curvature that I'm going to have here when I start introducing double bonds. Okay, so putting one double bond in here when I have oleic acid, have one kink in there. I move to linoleic acid, and I've got 2 double bonds there. So again, highlighting so we can make sure that we can see these pretty well here. There's a double bond there, and a double bond. Now, what I was showing you with my molecular structure there is this guy, linolenic acid. This is our omega-3 fatty acid. Here I'm going to have 1, 2, 3 double bonds there. Okay, and that starts really curving my structure. Okay, so again, saturated fatty acids, if I start putting, and I'm just going to use this finger here, if I start putting sort of 1 bend in, 2 bends, 3 bends, it's really going to start kinking that structure. Okay, so that when we build these all together into a triglyceride, so again, labeling what we have here, I'm still going to have that glycerol backbone. And what we're going to have here is the first part is going to look similar, right? Because we're still going to have saturated fats that we have there. But once we get down to the bottom part here, we really start having sort of some bent fingers, if you will. So here, and then we've got here, and then we've got there. What I really have is I have the inability to have these fingers sort of lay nicely, like when we have saturated fats that are there. So if we think about the same thing that we've talked about up above, when I introduce units of unsaturation, that is going to decrease the intermolecular forces that I'm able to have. That means I'm going to decrease my melting point, and these are going to be liquids at room temperature. And we define these as being oils. Sorry, my dogs are getting at my structures here. Okay, so labeling again what we know we have here. We have got an omega-6 fatty acid here, and omega-3 fatty acid here. So highlighting the important pieces we know when we have units of unsaturation: never before carbon 9, always in the cis configuration for what we tend to find naturally, and then never in conjugation. We have a separation with an sp3 hybridized carbon atom. Okay, so here we can see then how structure is going to afford function with our fatty acids being appended onto a glycerol backbone here to make our triglycerides. Just as a heads up, one of the exam questions that you definitely will see is I will ask you to build a triglyceride. You're going to need to know how to connect these pieces together, right? We're going to have an ester linkage between my glycerol backbone, and then this is going to be an ester linkage, and then you're going to have some description for a fatty acid that you'll have. Maybe it's a saturated fatty acid at carbon 1, and then it's an omega-6 at carbon 2, and an omega-3 at carbon 3. You're going to need to know how to put those pieces in. Importantly, you need to make sure to indicate that the geometry is going to be cis for any double bonds that you draw.